And we're finally on chapter 3, and now this gets into air temperature. So we've moved from energy transfer as heat and seasons into air temperature, and all of this obviously is related, and let's check it out how it is related. Think of each season as modeling a day for temperature. And if you look on this graph here, that season really starts with solar energy coming in and radiant energy coming in and transferring to the ground, since the ground heats the air and the air changes temperature. So if we look at a seasonal level of solar absorption and then temperature of the air during the season, we can really model that into a day. Let me explain a little bit more. At the beginning of a season, at the middle of June, for instance, on this chart, you'll see that in red is the amount of solar energy coming into the area. And you see that that soon peaks right around July. We're looking at average solar energy here. So while you would get maximum solar energy at the summer solstice because you have the longest and the longest day and the best angle, this is an average. So you're going to get a little bit of lag on there. But that's in red, and that's right here for the peak. That's very close to the beginning of the season for average solar, what's called insolation, or average solar energy to the earth. And then after that peak, it drops off through September. And what you notice here is that the temperature for the season starts out lower in late June at the solstice, then climbs to peaking right around late August, September, and then drops off again. So again, there's a lag between energy coming in and the temperature, also because the temperature is the average kinetic energy. So these averages really do factor into lags between them, but you can see that a season is like a day because we start out the morning at low temperatures, build through the late afternoon, and then drop off later on, much like a season. And this is important to us because it helps us to understand how we transfer energy from soil to the air over the course of a season and over the course of a day. And while water is probably most important for that transfer, we're going to study the transfer of energy first in soil, and then we'll get to water. When it comes to soil, we're looking at different factors of type of soil, sandy versus dark soil, moisture content, dry versus wet soil, and vegetative cover, densely covered trees and vegetation versus barren desert sandy soils. And we are looking at 3 different factors for transferring that energy. One is radiant energy, and how it is absorbed or how it is reflected. And then the second are phase changes in that soil. For instance, if it's moist soil, it can evaporate off that moisture to water vapor versus dry soil. And then conduction in the first few inches of that soil as well. I have a chart for that. And what it has is the type of soil, sandy or dark, the moisture content, dry or wet, and the vegetative cover, dense or barren, versus the radiation either reflecting or absorbing, any phase changes with wetness, and the conduction in the first few inches. So let's go over this. I realize it's dense, that's why I'm going over it with you. Sandy soil is going to obviously reflect more radiant energy because of its color than dark soil, which is going to absorb more radiant energy. You saw that in the lab of the shiny can versus the dark can. Let's go down here and talk about vegetative cover. And when we look at dense shady areas, they are shading the soil underneath them. So the soil is not going to be absorbing much energy. On the other hand, the vegetation is going to be absorbing an enormous amount of energy and photosynthesizing that to produce more water vapor and more oxygen for the environment. If you're looking at a barren area, think of Death Valley, you're going to have very little shading for that soil, and so that soil can absorb even more. When we talk about absorbing an enormous amount of energy, we're talking about dark soils that are barren. We're talking something like asphalt. Let's look at phase changes and energy transfer, because remember, if we have water to evaporate, while that water is evaporating, think of the kettle, that temperature of the kettle is not changing while the water is evaporating. The temperature of the soil is not changing while the water is evaporating out of the soil. So moist soils are really very important to maintaining a stable temperature during the season and during the day. And conversely, dry soils heat up very quickly because all of the energy that they absorb goes to changing temperature in the soil, because there's no phase change into evaporation. Finally, let's look at conduction, and we look at conduction of the sandy soil versus the dark soil. And in conduction, what is important to remember is conduction works from higher temperatures to lower temperatures. Think of putting the metal rod into the flame. The metal rod is conducting from the higher temperature of the flame to the lower temperature of your hand. That's the way conduction works. When you have reflective substances like sandy soil, they do not tend to heat up as quickly, so there's not that much of a differential between the temperature of the sand and the temperature of the air that's getting the reflection off the sand. The temperature of the air right above the sand is very warm because of the reflection of the sand. Not much of a differential there, not much conduction between the hot sand that's still reflecting and the reflection which has warmed the air right above the sand. Not much reflection there, but there is a lot of reflection, there is a lot of conduction between the dark soil, which has absorbed a lot of energy and effectively kept that energy from the layer of air right above the soil. So there's warm soil and cooler air, and there's conduction through there that really powers the convective parcels that move off of the warm soil. So convection is more efficient when it works with conduction, and conduction is more efficient when it works with dark soil. If you think about some of the hottest soil that we're talking about dark soil that absorbs a lot and dry soil that heats very quickly without the phase change, and barren soil that is not shaded at all. That's like an asphalt jungle, like in New York, which really holds onto its heat during the day as it absorbs it. And conversely, right behind this hottest soil is sandy soil that is dry and that is barren, obviously. So these are what really, what we talk about in terms of heat and transfer of heat. Now, when we look at a temperature lag for seasons and for days that is behind the energy transfer, for instance, what we noted back there is that the energy transfer is highest in June for the season. The energy transfer is highest at noon when the sun is right above us. But the temperature peak for the season is late August or September, the temperature peak for the day is late in the day, 3 and 4 o'clock. Why do you have that lag? Again, it goes back to the average that we're talking about. When we average things out, it lends itself to a lag. A temperature is an average kinetic energy only per molecule, whereas the solar energy transferred total energy, not only kinetic, but also potential energy. So that temperature lag is due in part to the fact that it's an average, and it's due in part to the fact that it's only kinetic energy that we're measuring. And conversely, I want to talk to you a little bit about temperature as an average and that lag. And the temperature also lags as a result of the fact that there's high specific heat for water in moist soils. So let's talk a little bit more about specific heat, because specific heat really drives the absorption of energy in our oceans, and our oceans really drive our seasonal outlook, and our seasonal temperatures. So let's talk about specific heat. Specific heat is the capacity of a substance to absorb the radiant energy from the sun, store it as potential energy, and emit it as radiant energy. Specific heat is all about radiant energy and how it is taken in by a substance. And specifically, it is the amount of energy to raise the temperature of that substance 1 degree Celsius. So it's a very specific energy measure, 1 degree Celsius. Water has the highest specific heat. We'll talk about why in a second. At 1 calorie, that's how we measure heat, 1 calorie per gram of water. When we talk about high specific heats, we're literally talking about the reluctance of the substance to absorb and to change temperature. So high specific heats are the reluctance of a substance to change temperature. Let's talk about that a bit. The specific heat of water at 1 calorie per gram for 1 degree Celsius change is much higher than the specific heat of soil, which is at 0.2 calories per gram per degree Celsius. So the specific heat of water is about 5 times greater than soil. Let's talk about why that is. It all has to do with molecular bonds in water. Water has the highest specific heat because water has bonds between molecules of water, which is an unusual hydrogen bond between molecules of water that hold it together. And not only that, but there are very strong covalent bonds between hydrogen atoms and oxygen atoms, and hydrogen atoms and oxygen atoms. So there's a lot of bonding in water that requires more energy to vibrate the system, put in the kinetic energy, and then to increase that kinetic energy and increase that average temperature, which is the average kinetic energy. A lot of bonding in there in water. In fact, if you compare specific heat energies, you're looking at water as being top. Wet soil has quite a high specific heat energy. It takes a lot of energy to warm wet soil. Dry soil, like I said, 0.2. Really easy to move that soil temperature up. And sand, even easier than dry soil to move that temperature up. As a result of water being near us and the fact that it takes so long to move that temperature up, it means that the summers stay cooler near the ocean, and it also takes longer for that energy to be lost out of the water, and it means that the winters are warmer by the ocean. That's it for us and seasons and daytime and specific heat and radiant energy. Let's go on to the next one.